80% of the universe is empty. Not empty the way a room is empty. Empty the way nothing is empty. Vast spheres of darkness stretching hundreds of millions of light years across where almost no galaxies exist, where no stars shine, where no light has traveled in billions of years. Scientists call them cosmic voids, and they are not just sitting there. In December 2024, a team of physicists published evidence that these voids have been fooling us, that the force we thought was pushing the universe apart, dark energy, 68% of everything that exists, might be an illusion created by the emptiness itself. That time runs 35% slower inside your galaxy than inside the void around it. That the expansion of the universe might not even be accelerating at all. And that we live inside one. Right now, tonight, we go inside the largest structures in the known universe. Structures that may erase dark energy from the textbooks, that are tearing the cosmic web apart, and that will eventually consume everything that exists. If you enjoy our calm nighttime journeys, remember to like and subscribe. We highly encourage our community to discuss the video topics in the comments and react to other comments. It is the most fun when we share our thoughts. Now, let us begin. Tonight, we are going somewhere that almost no one has been. Not to a distant star, not to the edge of a black hole. We are going to the emptiest place in the entire universe. A region so vast and so dark that if you were born at its center, you would live your entire life believing you were the only thing that existed. And when we return from that darkness, we are going to discover something that may shake the foundations of everything physicists thought they knew. Because inside these enormous bubbles of nothing, there may be an answer to the greatest mystery in modern science. An answer that could erase dark energy from the textbooks. An answer that could rewrite the fate of the cosmos itself. But first, we descend. Chapter 1. The Great Nothing. Imagine you are falling, not through air, not through water, but through space itself. There is no floor beneath you and no ceiling above. There are no stars, no distant galaxies glowing in the periphery, no nebulae painting color across the dark. There is only blackness. An absolute, featureless, consuming blackness that stretches in every direction for distances the human mind was never designed to comprehend. You are inside the Boots Void, and it is the loneliest place in the known universe. Discovered in 1981 by astronomer Robert Kirshner and his team at the University of Michigan, the Boots Void is a roughly spherical region of space, approximately 330 million light-years across. Its center sits about 700 million light-years from Earth in the direction of the constellation Boots, the herdsman. To call it empty would be an understatement so severe it barely qualifies as language. In a volume of space that size, you would expect to find roughly 2,000 galaxies based on the average density of the observable universe. The Boots Void contains approximately 60 galaxies where 2,000 should be. That is not a gap. That is not even a hole. It is a wound in the fabric of the cosmos. Kirshner and his colleagues were not looking for it. They were conducting a redshift survey, measuring how fast distant galaxies were moving away from Earth in order to build a three-dimensional map of the universe. Redshift is a beautifully simple concept. Because the universe is expanding, the farther away a galaxy is, the faster it recedes from us, and the more its light gets stretched toward the red end of the spectrum. By measuring that stretch, astronomers can calculate distance, and by plotting those distances across the sky, they can build a map. What Kirshner expected to find was the usual cosmic tapestry. Galaxies clustered here, thinner regions there, the standard large-scale structure that astronomers had been mapping for decades. What he found instead was a blank, a vast, spherical blank. A region of the sky where the galaxies simply stopped. The data showed a gap in galaxy velocities between roughly 12,000 and 18,000 kilometers per second. No galaxies, just emptiness. The team published their discovery in a letter to the Astrophysical Journal with a title that captured the bewilderment perfectly: "A million cubic megaparsec void in Boots?" Even they were not sure what they had found. Now, here is a detail that will change how you think about this void, and it comes from astronomer Greg Aldering. If the Milky Way had formed at the center of the Boots void instead of where it actually sits, humanity would not have discovered the existence of other galaxies until the 1960s. Think about what that means. For the entire history of our species, for every civilization that ever looked up at the night sky, for every astronomer who ever pointed a telescope at the heavens, the answer would have been the same: nothing. We would have believed we were alone. Not just alone on our planet, alone in the universe. Every star we could see would belong to our own galaxy, and nothing beyond it would be visible. The Milky Way would have been the universe, as far as anyone could tell. The discovery that other galaxies existed, that the cosmos was unimaginably vast and teeming with billions of island universes, would not have come until telescopes became powerful enough to reach across 300 million light-years of absolute emptiness to detect the faint glow of the nearest neighbor. The Boots void would not just have been lonely, it would have been a prison of ignorance. Now, before we go further, there is a misconception that needs addressing because it circulates constantly online, and it fundamentally misrepresents what a cosmic void actually is. If you search for images of the Boots void on the internet, you will almost certainly encounter a striking photograph of a perfect circle of blackness surrounded by stars. It looks like someone punched a hole in the night sky. It is dramatic, it is beautiful, and it is completely wrong. That image is Barnard 68. It is a dark nebula, a dense molecular cloud of gas and dust sitting inside our own galaxy, roughly 500 light-years from Earth. It is not empty at all. It is packed with material so thick that it blocks the light of every star behind it. It is an obstruction, like holding your hand in front of a lamp. The light is still there, you just cannot see it. A cosmic void is the opposite. It is not blocking anything. There is nothing to block. The light is not being hidden. It was never produced in the first place because the galaxies that should be there do not exist. A void is not an obstruction. It is an absence. And the difference between those two things is the difference between a curtain and a grave. So what exactly is a cosmic void? In the technical language of cosmology, a cosmic void is a region where the density of galaxies falls significantly below the cosmic average. Most voids range from about 20 to 50 million light-years across. The larger ones, the supervoids, can stretch 300 million light-years or more. They are not perfectly spherical. They are irregular, lumpy, often elongated. They are bounded by the filaments and walls of the cosmic web, the vast network of galaxies and dark matter that forms the largest structure in the observable universe. And here is the fact that will reshape everything you thought you knew about the cosmos. Voids are not the exception. They are the rule. They occupy roughly 80% of the volume of the observable universe. 80%. The galaxies, the galaxy clusters, the superclusters, the glowing filaments of the cosmic web. Everything you have ever seen in a Hubble photograph or a planetarium show or a textbook diagram of the cosmos represents the minority. The universe is not a collection of things with some gaps between them. It is a collection of gaps with things clinging to the edges. Imagine a bathtub full of soap bubbles. The thin, shimmering walls of those bubbles are where the galaxies live. The air inside the bubbles is the void, and the air vastly outnumbers the soap. That is the universe. Everything we have ever known, every star, every planet, every civilization that has ever existed or ever will exist, sits on the thin, fragile membrane between bubbles of nothing. The Sloan Digital Sky Survey one of the most comprehensive mapping projects in the history of astronomy, has identified over 8,000 voids and supervoids in the observable universe. And no matter how large a galaxy cluster gets, there always seems to be an even larger void sitting right beside it. The universe builds empires of light and then wraps them in kingdoms of darkness that dwarf them in every dimension. But these empty spaces are not just sitting there. They are not passive. They are not background. They may be the biggest lie in modern physics. Because the force that scientists believe is accelerating the expansion of the universe, the force called dark energy, the force that supposedly makes up 68% of everything that exists, might not be real at all. And cosmic voids might be the reason we have been fooled. That is where we are going next. Chapter 2. What if dark energy does not exist? In 1998, two independent teams of astronomers made a discovery that would earn them the Nobel Prize in Physics and fundamentally alter our understanding of the cosmos. They were studying Type 1, a supernovae, a particular kind of stellar explosion that always detonates with roughly the same intrinsic brightness. Because of that consistency, astronomers use them as cosmic measuring sticks. If you know how bright something truly is, and you can measure how bright it appears from Earth, you can calculate how far away it is. Simple geometry. The two teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rias, they were using these stellar explosions to measure how the expansion of the universe was changing over time. Everyone expected a straightforward answer. The universe was expanding, yes, but gravity should be pulling everything back together, slowing the expansion down like a ball thrown into the air, gradually losing speed. The ball was speeding up. The distant supernovae were dimmer than they should have been, farther away than the models predicted. The universe was not just expanding, it was accelerating. Something was pushing it apart, and that something was stronger than the combined gravitational pull of every galaxy, every star, every atom of matter in the entire cosmos. The discovery was so unexpected, so counter to everything physicists believed, that the teams initially thought they had made a mistake. They checked their data, they rechecked it, they checked it again. The result held. To explain this acceleration, physicists resurrected a concept that Albert Einstein had introduced in 1917 and later called his greatest blunder, a cosmological constant. An energy inherent to the vacuum of space itself, a repulsive force that pushes the fabric of the universe apart. They called it dark energy, and according to the best measurements available, it makes up approximately 68% of the total energy budget of the universe. More than matter, more than dark matter, more than everything else combined. Dark energy became the cornerstone of modern cosmology. It was built into the standard model of the universe, a framework known as lambda CDM, where lambda represents dark energy and CDM stands for cold dark matter. This model has been spectacularly successful at explaining the large-scale structure of the cosmos, the cosmic microwave background radiation, the distribution of galaxies, and the expansion history of the universe. It has passed test after test after test, but it rests on a critical assumption. An assumption that a physicist in New Zealand has been quietly challenging for nearly 2 decades. His name is David Wiltshire. He is a professor of physics at the University of Canterbury in Christchurch. And in December of 2024, he and his colleagues published an analysis in the monthly notices of the Royal Astronomical Society that sent a shockwave through the physics community. Using the Pantheon Plus supernova dataset, the most comprehensive catalogue of Type 1, a supernovae ever assembled, containing over 1,500 distinct stellar explosions, Wiltshire and his team tested an alternative to dark energy. They call it the timescape model. The idea is both simple and profound. The standard model of cosmology assumes that the universe, when viewed on the largest scales, is smooth and uniform. The technical term is the cosmological principle. It says that no matter where you are in the universe, if you zoom out far enough, everything looks roughly the same. Galaxies are distributed evenly. Space expands at the same rate everywhere. The equations that describe the universe are based on this assumption of smoothness. Specifically, they are based on a mathematical framework called the Friedmann equation, developed over 100 years ago, which describes how a perfectly uniform universe expands. But the universe is not smooth. It is lumpy. Spectacularly, dramatically, undeniably lumpy. It is riddled with galaxy clusters, cosmic filaments, enormous walls of galaxies, and above all, voids, vast empty voids that make up roughly 80% of its volume. And here is the key insight. Voids expand faster than dense regions. The reason is straightforward. In a region packed with galaxies, gravity is strong. It pulls matter together. It resists expansion. It slows things down. But inside a void, there is almost no matter, almost no gravity, nothing to resist the expansion of space. So the void expands freely, quickly, without restraint. And because voids dominate the universe by volume, the average expansion rate of the universe is weighted toward these fast, expanding, empty regions. Wiltshire argues that this is the source of the illusion. When astronomers measure the expansion of the universe and find that it appears to be accelerating, they are not detecting a mysterious repulsive force. They are detecting the natural consequence of living in a lumpy universe where most of the volume is expanding faster than the dense regions where galaxies actually sit. The acceleration is not real. It is a measurement artifact created by the uneven structure of the cosmos. In Wiltshire's own words, dark energy is a misidentification of variations in the kinetic energy of expansion, which is not uniform in a universe as lumpy as the one we actually live in. But the timescape model makes an even stranger prediction, one that sounds like it belongs in a science fiction novel rather than a peer-reviewed physics paper. Time itself runs at different speeds in different parts of the universe. This is not speculation. It is general relativity. Einstein proved that gravity slows time. We confirm this every single day with the Global Positioning System. The atomic clocks on GPS satellites, which orbit above most of Earth's gravity, tick slightly faster than identical clocks on the ground. If we did not correct for this difference, your GPS would drift by about 10 kilometers every day. Gravity slows time. That is not theory. That is engineering. Now apply that principle to the cosmos. Inside a galaxy cluster, where gravity is strong, time runs slower. Inside a cosmic void, where gravity is nearly absent, time runs faster. According to Wiltshire's calculations, a clock inside the Milky Way would tick approximately 35% slower than a clock placed at an average position inside a large cosmic void. That means billions more years have passed inside voids than inside the dense regions where galaxies cluster. Billions of years of extra time for space to expand. And that extra expansion, accumulated over the 13.8 billion year history of the universe, creates the appearance of acceleration without any dark energy at all. When the timescape model was first tested against supernova data in 2017, it performed only slightly better than the standard Lambda CDM model. But with the vastly improved Pantheon Plus dataset, the results shifted dramatically. The statistical analysis now shows what the team calls very strong evidence in favor of the timescape cosmology over the standard model. The Bayes factor, a mathematical tool used to compare competing theories, decisively favors the timescape interpretation. If Wiltshire is right, the implications are staggering. 68% of the universe, the portion attributed to dark energy, simply does not exist. The Nobel Prize-winning discovery of cosmic acceleration would not be overturned exactly, but reinterpreted. The data would still be valid, the supernovae would still be dim, but the explanation would be entirely different. Not a mysterious force pushing the universe apart, but a universe so lumpy and uneven that our measurements were fooled by the geometry of space-time itself. The European Space Agency's Euclid satellite, launched in July of 2023, and NASA's Nancy Grace Roman Space Telescope are now gathering the data that could settle this question definitively. Wiltshire himself has said, with new data, the universe's biggest mystery could be settled by the end of the decade. Whether dark energy is real or whether it is an illusion painted by the voids, there is a more unsettling question waiting. Because the void that might be fooling us is not somewhere far away. It is not in a distant corner of the observable universe. It is right here. We live inside one. And it may have broken the most important measurement in all of cosmology. Chapter 3. We live in a void. There is a region of space, roughly 2 billion light-years across, that contains far fewer galaxies than it should. It is not as dramatic as the Boots Void. It is not a perfect sphere of emptiness with only 60 galaxies where 2,000 should be. It is subtler than that, more insidious. The galaxy density in this region is estimated to be somewhere between 15 and 50% lower than the cosmic average, depending on which survey you consult and which wavelength you observe in. It has been detected in optical light, in near-infrared, in X-ray, and in radio wavelengths. Multiple independent observations across the electromagnetic spectrum point to the same conclusion. There is a hole, and we are inside it. It is called the KBC Void, named after the 3 astronomers who characterized it in 2013 using near-infrared galaxy counts: Ryan Keenan, Amy Barger, and Lennox Cowie. Some scientists call it the local hole. Others call it the local supervoid. Whatever you call it, the implication is the same. The Milky Way, our sun, our planet, our entire local group of galaxies, and a substantial portion of the Laniakea supercluster all sit within a few 100 million light-years of this void's center. Our cosmic neighborhood is not a bustling metropolitan center of the universe. It is a suburb on the edge of nowhere, surrounded by an ocean of diminished density that stretches 1 billion light-years in every direction. Now, this might sound like a cosmic trivia fact. Interesting, but not particularly consequential. But it is consequential. It may be the most consequential thing about our position in the universe. Because the KBC Void, if it is real and as large as the data suggests, could be responsible for one of the most vexing problems in all of modern physics: the Hubble tension. Here is the problem. The Hubble constant is a number that describes how fast the universe is expanding. It tells you how quickly galaxies are moving away from each other. And for decades, physicists have been trying to pin it down with ever-increasing precision. There are 2 main ways to measure it. The first method looks at the nearby universe. Astronomers use objects called Cepheid variable stars and Type 1a supernovae to build a cosmic distance ladder, measuring how fast galaxies near us are receding. This approach, refined over many years by Nobel laureate Adam Rees and his colleagues, gives a value of approximately 73 kilometers per second per megaparsec. That means, for every megaparsec of distance, which is about 3.26 million light-years, galaxies are moving away from us 73 kilometers per second faster. The second method looks at the ancient universe. Scientists study the cosmic microwave background, the afterglow of the Big Bang, the oldest light in existence. By analyzing the patterns frozen into that primordial glow, they can calculate what the expansion rate should be today. This approach, using data from the European Space Agency's Planck satellite, gives a value of approximately 67 kilometers per second per megaparsec. 73 and 67. Those numbers should be the same. They are measurements of the same thing, the expansion rate of one universe, and they disagree. At first, physicists assumed the discrepancy would go away as measurements improved. Instruments would get more precise. Systematic errors would be identified and corrected. The 2 numbers would converge. But the opposite happened. As the measurements became more precise, the gap became more statistically significant. It did not shrink, it hardened. Adam Riess himself has said, "Our measurements keep getting more precise, and the tension does not go away." This disagreement, this stubborn, inexplicable gap between two equally valid measurements of the same quantity, is called the Hubble tension. And it is not a minor footnote, it is a crisis. Because if both measurements are correct, then something is fundamentally wrong with our model of the universe. Something is off, something does not add up, and physicists have been tearing their hair out for years trying to figure out what it is. Enter the KBC Void. If we are sitting inside a large, underdense region of the universe, then the galaxies around us are not behaving the way galaxies in an average region of the cosmos would behave. Inside a void, there is less matter than normal, less gravitational pull holding things together. So the galaxies in our vicinity are being tugged outward, pulled toward the denser walls of the void where gravity is stronger. They are flowing away from the center of the underdensity and toward the edges. This means that when we measure the expansion rate using nearby galaxies, we are not measuring the true expansion rate of the universe. We are measuring the expansion rate plus an extra outward flow caused by our local environment. Our measurement is inflated, biased, contaminated by the void we happen to live in. Physicist Indranil Banik of the University of St. Andrews has calculated that the KBC void could raise the locally measured Hubble constant by approximately 11% compared to the true cosmic value. 11%. That is almost exactly the size of the gap between the two measurements. In January of 2025, Banik and his colleague Vasileios Kalaitsidis published an analysis testing the void hypothesis against 20 years of baryon acoustic oscillation data, which are ancient sound wave imprints frozen in the distribution of galaxies. The result was striking. The data favored a void model over a void-free model, consistent with the Planck cosmology by a factor of approximately 100 million to 1. 100 million to 1. That is not a marginal preference. That is a landslide. And it was presented at the Royal Astronomical Society's National Astronomy meeting in 2025, where it generated enormous attention. The idea is not without its critics. Other analyses using different methods have found smaller or differently shaped voids. Some find no significant underdensity at all. The debate is fierce and ongoing. But the KBC void hypothesis has refused to die, and with each new dataset, it seems to gain rather than lose momentum. Think about what this means. If the void explanation is correct, we are like fish in a fishbowl trying to measure the current of the ocean. Our bowl distorts everything we see. The water in our little bubble moves differently than the water outside, and we, trapped inside, have no way to know the difference unless we figure out that the bowl exists. The Milky Way moves at approximately 630 kilometers per second relative to the cosmic microwave background. That is not the expansion of space. That is our galaxy's actual motion through the universe. And part of that motion may be caused by the gravitational pull of the denser regions surrounding the KBC void, dragging us outward like a marble rolling toward the edge of a bowl. And here is the deepest implication. The standard model of cosmology, lambda CDM, predicts how lumpy the universe should be on various scales. It sets limits on how large and how empty a void can possibly be, given the initial conditions after the Big Bang and the known laws of physics. Moritz Hasselbauer and colleagues calculated that a void as large and as deep as the observed KBC void is inconsistent with the lambda CDM model at a significance level of 6 sigma. In physics, 5 sigma is the threshold for claiming a discovery. 6 sigma means the odds of the standard model producing the KBC void by chance are less than 1 in a billion. If the void is real, and this calculation is correct, then either the void is an extraordinarily unlikely fluke, or the standard model of cosmology is wrong, not slightly wrong. Not in need of minor adjustments. Fundamentally, structurally wrong in the way it describes how the universe builds its largest structures. Banach predicted that the resolution could arrive as soon as 2030, as next-generation surveys and telescopes provide the data needed to map the local universe with unprecedented precision. But for that to happen, he said, scientists must accept that the universe has more structure than expected in the standard cosmological model. His words were blunt. Our best theory of cosmology is wrong. That is a problem, but nature does not care about our theories. The KBC void may be fooling our Hubble measurements. The timescape model says voids are fooling us about dark energy, but there is one more anomaly, a cold scar on the oldest light in the universe. A mysterious chill aligned with a supervoid so massive that some scientists think it might be a bruise from another universe colliding with ours. Chapter 4: The Cold Spot. The cosmic microwave background is the oldest light in the universe. It was released roughly 380,000 years after the Big Bang, the moment when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. Before that moment, the universe was an opaque fog of charged particles. After that moment, it became transparent. Light flooded the cosmos, and that ancient light has been traveling ever since, stretched by the expansion of space from the blinding glow of a young universe to the faint microwave whisper we detect today. It fills every cubic centimeter of the observable universe. It has a temperature of about 2.725 Kelvin, just a few degrees above absolute zero, and it is almost perfectly uniform. Almost. Across the sky, the cosmic microwave background shows tiny fluctuations in temperature, regions that are slightly warmer than average and regions that are slightly cooler. These fluctuations are extraordinarily small. The typical variation is about 18 millionths of a degree, 18 microkelvins. These are the fingerprints of the quantum fluctuations that seeded the entire large-scale structure of the universe. Every galaxy, every cluster, every void, every filament of the cosmic web grew from these tiny temperature differences. They are the most important map humanity has ever made. But there is a blemish on that map. In the constellation Eridanus, in the southern galactic hemisphere, there is a region of the cosmic microwave background that is too cold. Not slightly too cold in the way that normal fluctuations create hotter and cooler patches, anomalously too cold. About 70 microkelvins below the average CMB temperature. That may sound tiny, but in a sky where the typical fluctuation is 18 microkelvins, 70 is enormous. It is roughly 4 times larger than the standard deviation. It extends across about 5 to 10 degrees of sky, and its statistical probability under the standard model of cosmology is less than 1%. It should not be there. The anomaly was first identified in data from NASA's Wilkinson Microwave Anisotropy Probe, known as WMAP, and later confirmed with exquisite precision by the European Space Agency's Planck satellite. It has been studied, debated, modeled, and argued over for more than 15 years, and it remains unexplained. Scientists call it the CMB cold spot. The leading conventional explanation involves a void. Not just any void. The Eridanus supervoid, one of the largest known underdensities in the observable universe. It is a massive elongated structure, roughly 1.8 billion light-years across, containing about 30% less matter than its surroundings. Its center sits approximately 2 billion light-years from Earth. The Dark Energy Survey, using gravitational lensing data, confirmed its existence and showed that it is the most prominent underdensity in the dark matter mass maps of that region of the sky. The connection between the supervoid and the cold spot works through a mechanism called the integrated Sachs-Wolfe effect. Here is how it works. When a photon from the cosmic microwave background enters a region of space with a gravitational well, like a galaxy cluster, it falls into that well and gains energy. As it climbs back out on the other side, it loses energy. In a static universe, the gain and the loss would cancel out perfectly. But our universe is expanding, and dark energy is stretching space. By the time the photon climbs out of the gravitational well, the well has become shallower because expansion has diluted it. The photon does not lose quite as much energy climbing out as it gained falling in. It emerges slightly blue-shifted, slightly warmer. Now flip that around. When a photon enters a cosmic void, it climbs a gravitational hill because the dense regions surrounding the void pull matter outward. The photon loses energy going in. When it comes out the other side, the void has become shallower because expansion has stretched it further. The photon does not gain back all the energy it lost. It emerges slightly redshifted, slightly cooler. This is the integrated Sachs-Wolf effect, and it should produce a slight cooling of the cosmic microwave background in the direction of the Eridanus supervoid. The math checks out in principle, but there is a problem. The Eridanus supervoid is big. It is among the largest underdensities ever catalogued, but it is not big enough. Standard calculations show that the integrated Sachs-Wolf effect from this supervoid can account for only about 10 to 20% of the cold spot's temperature depression. The void explains a fraction of the anomaly, not the whole thing. And there is a deeper puzzle. When astronomers look at other supervoids across the sky, supervoids that are comparable in size to the Eridanus structure, the integrated Sachs-Wolf signal they produce is about 5 times stronger than the standard lambda CDM model predicts. 5 times. That is not a small discrepancy. That is a factor of 5 mismatch between theory and observation. Either the model is wrong about how dark energy interacts with voids, or something else entirely is going on. In 2022, a team of researchers used CMB lensing data from Planck to test whether a large void located anywhere between us and the surface of last scattering could be the sole cause of the cold spot. Their conclusion was definitive. They ruled it out. No single supervoid, no matter how large, sitting between us and the ancient light, can produce the entire observed temperature dip. The supervoid hypothesis, taken alone, is dead as a complete explanation. So what is causing it? One possibility is statistical fluke. The cold spot might simply be an extremely rare random fluctuation. The universe is vast. Unlikely things happen. A 1 in 100 event will occur somewhere in a sky full of fluctuations. This is the least exciting explanation, but it is also the hardest to disprove. Another possibility, proposed in a 2024 study, involves a more local explanation. The Eridanus supergroup, a complex of 3 merging galaxy groups located relatively close to us, could be producing foreground effects that mimic the cold spot signal. These groups, NGC 1407, NGC 1332, and the Eridanus group itself, are in the process of merging into a future galaxy cluster, and their combined gravitational influence could create a subtle temperature decrement in the microwave background passing through their vicinity. But the most dramatic hypothesis is the one that keeps physicists up at night. Some cosmologists have proposed that the cold spot could be a cosmic bruise, an imprint left by our universe colliding with another universe in a multiverse scenario. The idea comes from a branch of cosmological theory that suggests our universe is one of many, a single bubble in an infinite foam of bubble universes. If 2 bubbles collide, the contact point could leave a mark on the cosmic microwave background, a circular or near-circular region that is slightly hotter or slightly colder than its surroundings, a bruise. The cold spot's shape, its size, and its anomalous depth are consistent with some models of bubble universe collisions. The hypothesis is not proven. It is not even close to proven. But it has not been ruled out, and the fact that the conventional explanations all fall short keeps this exotic possibility alive. The cold spot remains one of the most enduring mysteries in observational cosmology. It is a scar on the oldest light in the universe, and no one can explain where it came from. The supervoid aligned with it is real. The cooling it produces is real. But the numbers do not add up. Something else is contributing to that anomalous chill. Something we have not identified. Something we may not yet have the tools to understand. The cold spot, the Hubble tension, the dark energy question, they all point to the same conclusion. Voids are not passive features of the cosmos. They are not empty space waiting to be ignored. They are active participants in the evolution of the universe. They shape what we see. They distort what we measure. They may be fooling us about the fundamental nature of reality. And right now, they are winning. Because the voids are not just sitting there being empty. They are growing. They are merging. They are tearing the cosmic web apart. Chapter 5. The web is being torn apart. To understand what cosmic voids are doing to the universe, you first have to understand what the universe looks like on the largest scales. And it does not look the way most people imagine. Most people, when they picture the cosmos, imagine galaxies scattered through space like stars sprinkled across a tablecloth, random, evenly distributed. Some here, some there. No particular pattern. That is wrong. The universe has a structure, an immense, intricate, hauntingly beautiful structure that stretches billions of light years and connects everything to everything else. It is called the cosmic web, and it looks exactly like what the name suggests. Imagine a spider web built in 3 dimensions, on a scale that defies comprehension. Long, thin threads of galaxies and dark matter stretch across the cosmos, connecting dense knots where thousands of galaxies cluster together. Between those threads are vast empty spaces, the voids we have been exploring all night. The threads are called filaments. The knots are called clusters. The empty spaces are the voids. And together, they form a foam-like pattern that repeats throughout the entire observable universe. This is not theoretical, we can see it. The first clear evidence came in the 1980s, when Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics completed the first deep redshift surveys of the nearby universe. What they found astonished the astronomical community. Galaxies were not randomly distributed. They were arranged in sheets and walls, with enormous empty voids between them. Geller and Huchra identified what they called the Great Wall, a massive sheet of galaxies stretching over 500 million light-years across the sky. The bubbly, foam-like structure of the cosmos was revealed for the first time. Since then, surveys like the Sloan Digital Sky Survey and the 2-degree field galaxy redshift survey have mapped millions of galaxies and confirmed the cosmic web in extraordinary detail. We now know of over 8,000 voids. We can trace filaments for billions of light years. We can watch galaxies streaming along those filaments like cars on a highway, flowing toward the dense clusters where the threads intersect. The universe has an architecture, and it is magnificent, and it is being destroyed. Inside galaxy clusters and along the filaments of the cosmic web, gravity dominates. The combined mass of billions of galaxies and trillions of solar masses of dark matter holds everything together. Structures persist. They grow. They pull in more matter and become denser and more tightly bound. But inside the voids, the situation is reversed. There is almost no matter, almost no gravitational resistance. And in that near emptiness, dark energy is king. Think of it this way. Dark energy, whatever it truly is, pushes space apart. Gravity pulls matter together. In the dense regions of the cosmos, gravity overwhelms dark energy and structures hold. But in the voids, dark energy overwhelms gravity and space expands unchecked. The voids are quite literally where the accelerating expansion of the universe happens. They are not passive gaps. They are dark energy's workshop. The only regions of the cosmos where the repulsive force that may be pushing the universe apart can act without meaningful opposition. Even if you removed every last atom of matter from the deepest void, something would remain. The fundamental quantum fields that permeate all of space carry a small but real amount of vacuum energy. This energy is not nothing. It is the residual hum of the quantum world, the zero-point energy of empty space itself. And in the absence of matter and gravity, that hum becomes the dominant force. And the voids are not sitting still. They are expanding, actively, relentlessly, and with increasing confidence. As a void grows emptier, the dominance of dark energy within it grows stronger. The expansion accelerates. The void pushes outward against its walls, compressing the filaments and sheets of galaxies that surround it. Matter is squeezed into thinner and thinner structures. Filaments that were once robust highways of galaxies become fragile threads. Walls become membranes. The cosmic web, that magnificent architecture we just described, is being slowly dissolved from the inside out. And the voids are merging. Like soap bubbles combining into larger bubbles, neighboring voids merge when the wall of galaxies between them becomes too thin to sustain itself. The galaxies in that wall are pulled outward by the gravity of the denser structures on the other side, and the wall dissolves. Two voids become one. The Boots void itself is thought to have formed this way. There is evidence of a tube-shaped filament of galaxies running through its middle, a remnant boundary wall between the two or more smaller voids that merged to create the giant we see today. That filament is a fossil, a ghost of a wall that used to separate two smaller voids before they swallowed each other. And even as the web is being torn apart, astronomers are discovering that it is more dynamic and more complex than anyone imagined. In December of 2025, a team led by researchers at the University of Oxford used South Africa's Meerkat radio telescope to discover one of the largest rotating structures ever observed. A razor-thin chain of 14 hydrogen-rich galaxies embedded in a cosmic filament approximately 50 million light-years long, spinning coherently as a single structure. 14 galaxies, rotating together in a coordinated dance across a distance so vast that light itself would need 50 million years to cross it. Filaments do not just connect galaxy clusters, they spin, they funnel matter. They impart angular momentum to the galaxies that form within them. The cosmic web is alive with motion and energy and dynamism. But this dynamism is a losing battle. The filaments spin and the galaxies stream and the clusters grow, but the voids are growing faster. Every year, every million years, every billion years, the voids claim a little more territory. The filaments get a little thinner, the walls get a little more fragile. The dense regions become more isolated as the empty spaces between them expand. The cosmic web is not eternal. It is a transient structure, a brief flowering of complexity that exists only because gravity and dark energy are still roughly in balance. But the balance is shifting. Dark energy is winning. The voids are winning, and if you follow this process to its logical conclusion, not over centuries, not over millennia, but over timescales so vast they make the current age of the universe look like a single heartbeat. The result is the most terrifying vision of the future that science has ever produced. The cosmic web will dissolve, the filaments will snap, the clusters will become islands, and one by one, those islands will disappear beyond the cosmic horizon, their light redshifted into oblivion by the relentless expansion of the voids. The universe will not end with a bang. It will end with a silence made of nothing. And that silence is what we turn to next. Chapter 6. The Void Takes Everything. Let us talk about the future, not the near future, not the future of next year or next century, or even the next million years. Let us talk about the future on a scale so enormous that the word future barely applies. Let us talk about what happens to the universe when the voids finish their work. Right now, the Milky Way and the Andromeda Galaxy are falling toward each other at approximately 110 kilometers per second. In roughly 4 to 5 billion years, they will collide and merge into a single enormous elliptical galaxy that astronomers have nicknamed Milky Way. This merger will be one of the last great events in our cosmic neighborhood, because by the time it happens, something far more consequential will already be underway. The voids will be consuming the web. As dark energy continues to drive the expansion of space, the voids will grow larger and more dominant. The filaments that connect galaxy clusters will stretch and thin. The walls of galaxies that define the edges of voids will be pulled apart. The dense clusters that sit at the intersections of the cosmic web will become increasingly isolated as the space between them expands faster than light can cross it. Within roughly 100 billion years from now, every galaxy beyond our own merged local group will have crossed what is called the cosmic horizon. That is the distance beyond which the expansion of space exceeds the speed of light. Galaxies beyond the horizon are not moving faster than light through space. Space itself is expanding between us and them faster than any signal can traverse it. Light from those galaxies will never reach us again. Their photons will be stretched to infinite wavelength. They will become invisible. And to any observer in Milky Way looking up at the sky, the universe will appear to contain exactly one galaxy, theirs. The rest of the cosmos will be gone, not destroyed, not exploded, simply unreachable, invisible, functionally non-existent. The night sky will be dark. Not the kind of dark we experience now, where faint galaxies hide beyond the reach of the naked eye, but can be found with a telescope. Truly dark, permanently dark. No telescope, no matter how powerful, will be able to detect anything beyond the merged galaxy. The observable universe will shrink to a single island of light, floating in an infinite sea of expanding emptiness. And then the island itself will begin to die. Star formation requires fuel, hydrogen gas, the raw material from which stars are born, and that fuel is finite. The Milky Way, Andromeda, and all the galaxies in the local group contain a limited supply of gas. As new stars are born, the supply diminishes. Some gas is locked up in stars forever. Some is expelled into space but recycled less and less efficiently over time. On a timescale of roughly 1 trillion years, the fuel runs out. The last new stars are born. And from that point on, the only light in the universe comes from the slowly cooling embers of an aging stellar population. Red dwarfs, the smallest and most miserly stars in the cosmos, will be the last to burn. They consume their hydrogen so slowly that the very smallest of them can shine for trillions of years. But even they have an expiration date. After perhaps 10 to the 14th years, 10 followed by 14 zeros, a number so large it has no intuitive meaning, the last red dwarf will exhaust its fuel and fade to black. What remains is a graveyard. White dwarfs cooling to the temperature of the void. Neutron stars spinning down to silence. Black holes swallowing the last scraps of matter in their vicinity, and then sitting alone in the darkness, slowly, inconceivably slowly, evaporating. Stephen Hawking showed in 1974 that black holes are not truly eternal. They radiate energy at an unimaginably slow rate through a quantum process now called Hawking radiation. A black hole with the mass of our Sun would take roughly 10 to the 67th years to evaporate. A supermassive black hole at the center of a galaxy would take 10 to the 100th years. That number is a 1 followed by 100 zeros. It is called a googol, and on a timescale that dwarfs even a googol, the last black holes will vanish in a final faint puff of radiation, and the universe will contain nothing but a diffuse bath of photons, neutrinos, and perhaps the occasional stray electron or positron, all separated by distances so vast that no two particles will ever interact again. This is the heat death of the universe. It is the state of maximum entropy, maximum disorder, maximum equilibrium, no energy gradients, no temperature differences, no structure, no complexity, no possibility of anything ever happening again. The universe reaches a state indistinguishable from nothingness, not because matter has been destroyed, but because it has been diluted to such an extreme degree that it might as well not exist. The Boots Void is not an anomaly. It is a prophecy, a preview of what everywhere will look like given enough time. The loneliest places in today's universe are a dress rehearsal for the fate of the entire cosmos. But there is an even darker possibility. The heat death scenario assumes that dark energy is constant, that the cosmological constant remains the same forever, that the repulsive force driving the expansion stays steady and unchanging. But what if it does not? What if dark energy is not constant, but grows stronger over time? Physicists call this phantom energy. And if it exists, the end of the universe is not a slow, gentle fade into nothingness. It is a rip. In the Big Rip scenario, the expansion of space accelerates without limit. First, the voids grow so aggressively that they tear apart galaxy clusters. Galaxies that have been gravitationally bound for billions of years are ripped away from each other. Then, individual galaxies are disrupted, their stars flung into the expanding void like sparks from a disintegrating campfire. Then solar systems are torn apart as the expansion overwhelms the gravity, binding planets to their stars. Then planets themselves are shredded. Then atoms. The force holding electrons to their nuclei is overpowered by the expansion of space. In the final fraction of a second before the end, even atomic nuclei are ripped apart. The universe does not fade. It is shredded, disassembled, unmade. The Big Rip is not settled science. It depends entirely on what dark energy actually is and whether its strength changes over time. But the latest data from the Dark Energy Spectroscopic Instrument, DESI, released in April of 2024, showed hints that dark energy may indeed be evolving, not constant, but changing. The signal is not yet definitive. More data is needed, but the possibility that dark energy is growing stronger, that the Big Rip is not just a theoretical nightmare, but a genuine possibility, remains uncomfortably alive. Whether the end comes as a slow fade or a violent unraveling, the instrument of that end is the void. The voids are where expansion happens. The voids are where dark energy dominates. The voids are what will consume the cosmic web and isolate every structure in the universe until nothing is left but emptiness stretching in every direction forever. The universe is dying, and the voids are the instrument of its death. But hidden in the deepest darkness, in the most isolated corners of the cosmic web, there are survivors. Tiny, lonely blue galaxies that time forgot. Galaxies that have been evolving in near-perfect isolation for billions of years, untouched by the violent mergers and crowded environments that shaped the rest of the cosmos. And in the dying universe we have just described, these forgotten galaxies may be the only places where the lights stay on, the last refuge for any mind desperate enough to seek them out. Chapter 7: The Loneliest Galaxies in the Universe. After everything we have discussed tonight, the existential dread of an expanding void consuming all structure, the crisis in physics, the possibility that the universe is fooling us about its own nature. Let us slow down, let us take a breath, and let us visit something quiet and beautiful. Deep inside the cosmic voids, far from the glowing highways of the cosmic web, there are galaxies, not many. Not the grand spirals and massive ellipticals that dominate the galaxy clusters. These are smaller, bluer, quieter. They sit alone in the darkness, separated from their nearest neighbors by tens of millions of light years of nearly perfect emptiness. They form stars slowly and peacefully, without the violent collisions and gravitational harassment that shape galaxies in denser environments. They are the loneliest galaxies in the universe, and they are among the most fascinating objects in all of astronomy. Void galaxies represent only about 5 to 10% of all galaxies. They are fundamentally different from their counterparts in the crowded regions of the cosmos. In galaxy clusters, galaxies live turbulent lives. They collide with each other. They merge. They have their gas stripped away by the hot intracluster medium through a process called ram pressure stripping, where the diffuse gas between galaxies in a cluster acts like a wind, blowing the cold gas right out of any galaxy that moves through it. Without gas, a galaxy cannot form new stars. It ages, it reddens, it dies. This is why the largest galaxies in the centers of clusters tend to be giant red ellipticals. They have been through so many mergers and lost so much gas that star formation has ceased entirely. They are the retired titans of the cosmic web, massive but inert. Void galaxies have experienced none of this. In their isolation, they have been left alone to evolve according to their own internal rhythms. No collisions, no mergers, no gas stripping. Just a quiet, uninterrupted existence stretching back billions of years. And the result is striking. The Cavity Project, the Calar Alto Void Integral Field Treasury Survey, a major observational program studying galaxies inside voids, has confirmed that void galaxies have lower stellar mass surface density, younger stellar populations, and higher rates of star formation relative to their mass compared to galaxies in denser environments. They are forming stars more actively but more calmly. Without the violent triggers of mergers, their star formation proceeds at a gentle, steady pace, fueled by the gas they have retained precisely because no one has been around to take it from them. Simulations using the Illustris TNG framework, one of the most sophisticated cosmological simulations ever run, show that the dark matter halos around void galaxies assemble their stellar mass more gradually than halos in dense environments. Some low-mass void galaxies were still actively accumulating excess mass as recently as 2 billion years ago. They are not behind. They are not failed galaxies. They are galaxies frozen in an earlier stage of evolution, developing at their own pace, undisturbed by the frantic activity of the cosmic web. And this isolation makes them extraordinarily valuable to science. When astronomers study galaxies in clusters, they see the combined result of internal processes and external influences. Nature and nurture tangled together in ways that are almost impossible to separate. Was that galaxy red because it ran out of gas on its own, or because ram pressure stripping stole its gas? Did it form that unusual shape because of internal dynamics, or because of a collision 3 billion years ago? In dense environments, the answers are always complicated. Void galaxies strip away the complications. They are the closest thing astronomers have to a control group. Galaxies evolving in near isolation, driven almost entirely by their own internal physics. By studying them, scientists can understand what galaxy evolution looks like without the noise of the environment. They reveal the fundamental nature of galaxies themselves, separated from the accidents of their surroundings. The Void Galaxy Survey studied approximately 60 galaxies in the deepest interiors of voids identified by the Sloan Digital Sky Survey. What they found was remarkable. Many of these galaxies showed signs of cold gas accretion, pristine hydrogen flowing into the galaxy directly from the void's interior, along faint tendrils of the cosmic web that penetrate even into the emptiest regions of space. One galaxy in particular stands out. VGS-12, a polar ring galaxy sitting deep inside a void. A polar ring galaxy is a rare and beautiful structure. It has two distinct planes of rotation, a central disk spinning one way, and a ring of gas and stars orbiting around it at nearly 90 degrees, like the rings of Saturn turned perpendicular to the planet's equator. VGS-12 appears to be actively accreting metal, poor, pristine gas directly from a nearby void filament. The chemical composition of the infalling gas, confirmed by measurements published in early 2026, matches what you would expect from primordial material that has never been processed through the nuclear furnaces of stars. It is gas that has remained essentially unchanged since the early universe. This is one of the very few individual galaxies where scientists have found convincing evidence of direct cold gas accretion from the cosmic web. Not theoretical, not simulated, observed. A galaxy in the void, quietly drinking from the thinnest thread of the cosmic web, building itself from material as old as the universe itself. And then there is NGC 6789. NGC 6789 is a blue, compact dwarf galaxy. It sits alone in the local void, a relatively nearby underdensity in our cosmic neighborhood, about 12 million light-years from Earth. It is small. It is isolated. It has no significant neighbors for millions of light-years in any direction, and it is burning with the light of new stars. In 2025, a team of astronomers used deep imaging from Spain's 2-meter twin telescope to study this galaxy in extraordinary detail. They were looking for tidal features, the faint streams and tails of stars that are ripped from a galaxy during a gravitational encounter with a neighbor. Tidal features are the scars of interaction. They tell you that a galaxy has not been alone, that something else came close and pulled at its stars. They found nothing. No tidal features, no merger remnants, no evidence of any external influence whatsoever. NGC 6789's central starburst, the furious activity at its core, where roughly 4 million solar masses of material are being forged into new stars, was triggered entirely by internal processes. Perhaps the accretion of pristine gas from the void itself. Perhaps an instability in its own gas disk. Whatever the cause, this galaxy is building new stars entirely on its own, with no help and no interference from anything else in the cosmos. It is a firefly in the cosmic dark, a tiny spark of blue light burning in the middle of millions of light-years of nothing, the loneliest factory of stars we know. There is something profoundly moving about these void galaxies. They did not choose isolation. They were born in the emptiest regions of the universe by the random chance of quantum fluctuations 13.8 billion years ago. They have spent their entire existence far from the action, far from the grand collisions and mergers and violent events that shaped the galaxies we usually celebrate. And yet, they endure, they form stars, they grow, they evolve, quietly, patiently, on their own terms. They are not just beautiful, they are survivors, and in the dying universe we described in the last chapter, these lonely blue galaxies may turn out to be the most important structures in all of existence. Because when the cosmic web has been torn apart, when the clusters have gone dark, when the last great galaxies have exhausted their fuel and faded to silence, the void galaxies will still be there, still forming stars, still glowing, still alive. The last refuge in a universe of darkness, and that is exactly what we explore next. Chapter 8: The Last Refuge. The universe is already dying. That is not a prediction. It is a measurement. The peak era of cosmic star formation occurred roughly 10 to 11 billion years ago, when the universe was only about 3 billion years old. Back then, galaxies were furiously converting hydrogen into stars at a rate many times higher than today. The cosmos was young and bright and burning with creative energy. Since that peak, the rate of star formation across the universe has been declining steadily. A comprehensive survey called the Galaxy and Mass Assembly Project, known as GAMA, measured the energy output of the universe across 21 different wavelengths and concluded that the universe is producing roughly half as much energy as it did 2 billion years ago. The lead researcher described it simply: the universe is slowly dying. In the dense environments of galaxy clusters, this decline has been accelerated by the very processes that make clusters so dynamic. Mergers exhaust gas supplies. Ram pressure stripping blows fuel out of galaxies as they plunge through the hot intracluster medium. Tidal interactions between close neighbors distort gas reservoirs and trigger violent bursts of star formation that consume fuel in a single extravagant spasm rather than rationing it across billions of years. The result is galaxy quenching. One by one, the galaxies in clusters run dry. Their star formation ceases. They turn red. They go quiet. The most massive clusters in the universe are already dominated by these dead and dying galaxies. Giant red ellipticals coasting on the fading light of ancient stars with no fuel left to make new ones. But the void galaxies are different. Their isolation has been their salvation. Without mergers to trigger wasteful starbursts, without ram pressure to strip their gas, without tidal interactions to disturb their reservoirs, void galaxies have held onto their fuel. They are gas-rich. They are forming stars, slowly, calmly, sustainably. Their dark matter halos are shallower, meaning the feedback mechanisms that in denser environments can heat gas and prevent it from collapsing into stars are less efficient. More pristine metal, poor gas survives in their reservoirs, available for star formation over extraordinarily long timescales. The void galaxies are not just surviving, they are conserving. They are the universe's most efficient stewards of their own resources. While the cluster galaxies burn bright and burn out, the void galaxies burn low and burn long. And on the timescales we discussed in the last chapter, the timescales of trillions of years, that difference becomes everything. Consider what the universe will look like 100 trillion years from now. The cosmic web has dissolved. The filaments are gone. The great galaxy clusters have long since merged into singular, massive structures, and those structures have been isolated beyond the cosmic horizon. Each surviving galaxy or galaxy group exists in a pocket of space from which nothing else is visible. The sky is dark in every direction. In the former cluster regions, star formation ceased trillions of years ago. The last red dwarfs are sputtering out. The dominant objects are cooling, white dwarfs slowly fading toward invisibility, neutron stars spinning down into silence, and black holes drifting through the dark, consuming whatever scraps of matter drift close enough to fall in. These are the galactic graveyards. Vast collections of stellar corpses floating in an eternal night with no prospect of renewal is less than #0. 5# is greater than, but somewhere out there, in the deep void, a blue galaxy still glows. Not brightly, not the way galaxies glow today, but faintly, stubbornly, persistently. A small gas-rich dwarf galaxy that has been forming stars at a trickle for trillions of years, rationing its hydrogen with an efficiency that the profligate cluster galaxies never achieved. Its stars are small and cool, red dwarfs mostly, the most fuel-efficient engines the universe has ever produced. Some of them have been burning since before the cosmic web dissolved. Others are being born right now, in the last chapter of the universe's story, from gas that has been falling into this galaxy, from the thinnest remnants of the void's internal structure, for eons beyond counting. The last stars in the universe will almost certainly be born in void galaxies. They are the embers that will glow longest after the cosmic fire goes out. Now imagine a civilization, not our civilization, a civilization 100 trillion years from now, born on a planet orbiting one of the last living stars in a cluster galaxy. Their star is dying. Their galaxy is a graveyard. Every other star they can see is a cooling cinder. They know, because they are intelligent and they have physics, that their star will exhaust its fuel within a few billion years, and that when it does, there will be no replacement, no new stars, no new planets, no new chances. And then their astronomers detect something, a faint blue speck in the immense darkness. Not a star, a galaxy, a void galaxy, still forming stars, still warm, still alive, millions of light years away across a void that is actively expanding beneath their feet. Could they reach it? The journey would be almost inconceivably difficult. The void between them and their destination is not just empty, it is expanding. Space itself is stretching the distance faster than any conventional propulsion could close it. To cross a void that is actively growing, you would need either a speed close to that of light or a technology that circumvents the expansion of space entirely. Neither is within our current understanding of physics. But desperation has a way of rewriting what is possible. A civilization facing extinction, a civilization with trillions of years of accumulated knowledge and technology, a civilization with nothing left to lose, might attempt things that would seem absurd to us. Generation ships that travel for millions of years, propulsion systems that harness the energy of dying stars, perhaps even manipulation of space-time itself, if the physics allows it. We do not know if such a journey would be possible. The honest answer, given our current understanding, is probably not. The expansion of the void would likely outpace any achievable velocity, stretching the finish line farther away with every passing moment. The blue galaxy would remain visible, but unreachable, a mirage in the desert of space-time. But the image persists, a tiny ship crossing an ocean of nothing, heading toward the last light in the universe, the last act of intelligence in the cosmos, a race against expanding emptiness toward the final firefly in the dark. The void is both the prison and the refuge. It is the force that isolates everything, and the environment that preserves the last flickering remnants of star formation. The same emptiness that dooms the universe to heat death also creates the conditions where the last stars are born. The void giveth, and the void taketh away. But to truly understand why, to understand the strange physics of these empty spaces, we need to look more carefully at what happens at the edge of a void. Because voids do not just sit there being empty. They actively trap and repel. They are in a very real sense the universe's most impossible gravity traps. And the physics of how they work is far stranger than you might expect. Chapter 9. The Impossible Gravity Trap. Gravity is the most familiar force in the universe. You feel it right now, pulling you toward the center of the Earth. It is the force that keeps your feet on the ground, that holds the moon in orbit, that binds galaxies together across millions of light years. And the rule is simple. Everything with mass attracts everything else with mass. The more massive an object, the stronger its pull. The closer you are, the stronger the attraction. Newton figured this out in the 1600s. Einstein refined it in 1915. The basic principle has not changed. Mass attracts mass. Now apply that principle to a cosmic void. Inside a void, there is almost no mass. The density of galaxies and dark matter is far below the cosmic average. But surrounding the void, in the filaments and walls and clusters of the cosmic web, mass is concentrated. Dense knots of galaxies and enormous reservoirs of dark matter line the edges of the void like a gravitational fence. Here is the counterintuitive part. Because the void is nearly empty and the walls are dense, gravity pulls everything outward, away from the center of the void, toward the walls. Any galaxy sitting inside a void feels the gravitational tug of the dense cosmic web on all sides. And because there is almost nothing inside the void to pull it back toward the center, it drifts outward. Slowly, steadily, inevitably, it migrates toward the nearest wall. The void is not pulling things in, it is pushing them out. Or more precisely, the dense regions surrounding the void are pulling everything toward themselves, and there is nothing inside the void to compete. Think of it like a valley between mountains. If you place a ball on the slope, it rolls downhill toward the valley floor. But in a cosmic void, the geometry is reversed. The void is the hilltop, and the walls are the valleys. Mass rolls away from the void and toward the dense regions. The emptier the void gets, the steeper the gravitational hill becomes, and the harder it is for anything to remain inside. This is why galaxies stick to the walls of voids, like reflections on the surface of soap bubbles. They are not floating inside the bubbles. They are clinging to the membranes. Gravity pins them there. The void's edge is a gravitational cliff, and matter flows in only one direction: out. The few galaxies that do exist inside voids are sitting on the faintest tendrils of dark matter that penetrate into the void interior. These are not the robust filaments of the cosmic web that connect massive galaxy clusters. They are gossamer threads, thin, wispy structures that are straighter and simpler than filaments in dense regions. Because there are fewer gravitational distortions to bend them, they form the skeleton of the void, a faint echo of the larger cosmic web structure rendered in miniature. Recent simulations using the Illustris TNG framework have revealed that void interiors are not truly featureless. They contain their own intricate substructure, smaller voids nested inside larger voids. Voids within voids within voids. A fractal-like hierarchy of emptiness that mirrors the fractal-like hierarchy of density in the cosmic web. The universe's structure is self-similar at every scale. Dense regions contain smaller dense regions within them, and empty regions contain smaller empty regions within them. The pattern repeats from the scale of galaxy clusters down to individual galaxy halos, and from supervoids down to the tiniest pockets of underdensity. The Hercules void, studied in detail by the Cavity Project, appears to be expanding in all three spatial directions simultaneously, with essentially no detectable dark matter in its interior. It is one of the purest, pristine volumes in the local universe. A region of space so thoroughly evacuated by gravity and expansion that it approaches the theoretical ideal of perfect emptiness. Now here is a thought experiment. Could you fly into a void? If you had a sufficiently powerful spacecraft, could you leave your home galaxy, cross the boundary wall, and enter the void interior is less than #0. 3# is greater than. Technically, yes. The hardest part would be escaping the gravity of your own galaxy and the surrounding cosmic web. Once free, nothing physically prevents you from entering a void. There is no barrier, no wall of energy, no force field at the boundary. Just a gradual thinning of matter as you cross from the dense wall into the underdense interior. The transition would be smooth and unremarkable from a physical standpoint. But from an experiential standpoint, it would be unlike anything a human being has ever experienced. As you move deeper into the void, the galaxies around you would become fewer and fainter. The cosmic web, that intricate latticework of light and structure, would fade behind you like a city disappearing in the rearview mirror. Eventually, you would reach a point where no galaxy is visible in any direction. Not because they are too faint, because they are too far away. The nearest galaxy might be tens of millions of light years behind you. The nearest galaxy ahead might be tens of millions of light years in front, and in every other direction, nothing. You would be the most isolated object in the observable universe, more isolated than any void galaxy, because even void galaxies sit on faint tendrils of dark matter, connecting them, however tenuously, to the larger structure. You would be floating free in the purest vacuum the cosmos has to offer. Why would anyone do this? There is no practical reason, no resources to extract, no worlds to explore, no signals to detect. The void offers nothing, unless you want to hide. If a civilization needed to disappear, to remove itself from the sight and reach of every other intelligence in the cosmos, the interior of a cosmic void would be the ultimate hiding place. No light would reach you from the outside. No gravitational signal would betray your position. No electromagnetic emission from your technology would reach any detector in the distant cosmic web for tens of millions of years. You would be invisible, unreachable, forgotten. What would drive a civilization to seek such total isolation? Fear, perhaps. A universe full of unknown intelligences, some potentially hostile, might make the void seem appealing, or desperation. A civilization fleeing some cosmic catastrophe might see the void as the only safe harbor, or philosophy. A civilization that had concluded that existence is suffering might retreat into the void to minimize its interaction with the cosmos entirely. This connects back to the last refuge we discussed in the previous chapter. The void is simultaneously the most terrifying and the most protective environment in the universe. It will eventually consume everything. But until it does, it offers something no other environment can: perfect solitude. Voids are growing, merging, and consuming the cosmic web. They trap galaxies on their walls and evacuate their interiors with gravitational efficiency. They contain their own internal structure, a fractal hierarchy of emptiness within emptiness, and they offer, for any entity capable of reaching them, the most absolute isolation the universe can provide. But where did they come from? To answer that, we need to rewind the clock, not just to the formation of galaxies, not just to the birth of the first stars. We need to go all the way back to the first fraction of a second after the Big Bang itself, to a moment when a quantum hiccup smaller than an atom planted the seed of every void that exists. Chapter 10. Born from Quantum Whispers. 13.8 billion years ago, give or take a few million, the universe began. Not in an explosion, despite what the name Big Bang implies. There was no detonation. There was no center. There was no shockwave rippling outward through pre-existing space. Space itself came into being. Time itself came into being. And in the first fraction of the first second of existence, everything that would ever happen was set in motion by the tiniest imaginable imperfections. In the earliest moments after the Big Bang, the universe was an extraordinarily hot, extraordinarily dense, extraordinarily uniform plasma. Protons, neutrons, electrons, and photons all jammed together in a seething fog so dense that light could not travel more than a microscopic distance before being scattered. The temperature was billions of degrees. The density was unimaginable, and the whole thing was almost perfectly smooth. Almost. Quantum mechanics, the branch of physics that governs the behavior of the smallest particles, contains a principle that makes perfect smoothness impossible. It is called the Heisenberg uncertainty principle. It states that you cannot simultaneously know the exact position and momentum of a particle. There is always a fundamental fuzziness, a built-in randomness at the smallest scales. This is not a limitation of our instruments. It is a property of reality itself. Nature is, at its foundation, probabilistic. This means that even in the first instant of the universe's existence, when everything should have been perfectly uniform, there were tiny, random fluctuations, microscopic variations in energy density. Regions where the plasma was just barely denser than average, and regions where it was just barely less dense. The differences were mind-bogglingly small, roughly 1 part in 100,000. If the average density was a number like 100,000, then the fluctuations were a variation of about 1, up or down. Slightly more here, slightly less there. Then inflation happened. In the first tiny fraction of a second, the universe underwent a period of exponential expansion, so violent and so rapid that those microscopic quantum fluctuations were stretched to cosmic scales. Variations that had existed on scales smaller than an atom were suddenly spread across light years, then millions of light years, then billions. The quantum whispers of the newborn universe were amplified into the seeds of everything. We can see these seeds. The cosmic microwave background that ancient light released 380,000 years after the Big Bang carries the imprint of those primordial fluctuations frozen into its temperature patterns. The slightly warmer spots on the CMB map correspond to regions that were slightly denser in the early universe. The slightly cooler spots correspond to regions that were slightly less dense. Those tiny temperature differences, those delicate mottled patterns on the oldest photograph in existence, are the blueprint of the cosmic web. Every galaxy cluster, every filament, every void that exists today grew from those quantum whispers. The process of growth was straightforward in principle, but took hundreds of millions of years to play out. Gravity did the work. Regions that were slightly denser than average had slightly stronger gravitational pull. They attracted more matter from their surroundings, becoming denser still. The denser they got, the stronger their gravity, and the more matter they attracted. It was a runaway process. The rich got richer. Meanwhile, the slightly underdense regions experienced the opposite. With less mass, they had weaker gravity. Matter flowed away from them, pulled toward the overdense regions. As they lost mass, their gravity weakened further, and more matter escaped. The poor got poorer. Over hundreds of millions of years, this gravitational amplification transformed the nearly uniform early universe into the structured cosmos we see today. The overdense patches collapsed into filaments, walls, and clusters. The underdense patches expanded into voids. The cosmic web emerged from the quantum noise of creation like a sculpture emerging from a block of marble. The sculptor was gravity, the marble was hydrogen, and the chisel marks of quantum uncertainty determined where every mountain and every valley would form. The voids formed first at small scales and then grew. Small underdensities expanded and merged into larger ones, which merged into still larger ones. This is called the void-in-void hierarchy, and it mirrors the hierarchy of structure formation in the dense regions. Just as small galaxy groups merged into clusters, and clusters merged into superclusters, small voids merged into larger voids, which merged into supervoids. The Boots void, that 330 million light-year sphere of near emptiness, is thought to be the product of exactly this process. It did not form as a single, enormous underdensity in the early universe. It formed as several smaller voids that expanded and eventually combined. The evidence for this lies in the tube-shaped filament of galaxies that runs through the void's interior, a structure that makes no sense if the void formed as a single entity, but makes perfect sense as the remnant wall between two or more smaller voids that merged. That filament is a boundary marker, a scar left by the merger, a wall that once separated two voids and was partially dissolved when they combined, leaving behind a ghostly thread of galaxies suspended in the middle of the great nothing. This hierarchical merging process means that voids grow over cosmic time. They are not static features stamped into the universe at birth. They are dynamic growing structures that continuously eat into the walls and filaments around them. Like soap bubbles in a bathtub combining into larger and larger bubbles, the voids of the cosmos merge and expand with every passing epoch, and as they grow, the cosmic web between them thins. There is something profound about tracing the origin of the largest structures in the universe back to the smallest possible scale. The Boots void, 330 million light-years across, began as a quantum fluctuation, smaller than a proton. The cosmic web, stretching billions of light-years across the observable universe, was seeded by random variations in a plasma that was hotter than the center of any star. The largest emptiness and the smallest uncertainty are directly connected by an unbroken chain of cause and effect that stretches across 13.8 billion years of cosmic history. Everything we have discussed tonight, the dark energy crisis, the Hubble tension, the cold spot, the death of the cosmic web, the lonely void galaxies, the last refuge in a dying universe, all of it traces back to those first quantum whispers. If the fluctuations had been slightly different, if the random dice of the Heisenberg uncertainty principle had fallen slightly differently, the voids would be in different places, the filaments would follow different paths, and the universe would be a different place, perhaps a place with no Milky Way, no sun, no Earth, no one to wonder about the emptiness between the stars. The universe built itself from randomness, and from that randomness, it built a vast web of galaxies stretching billions of light-years, a web we have only recently learned to see. And what we found was far stranger and more beautiful than anyone expected. Chapter 11. A Universe of Bubbles. Before the Great Redshift surveys of the 1980s, most astronomers assumed that galaxies were spread more or less evenly throughout the cosmos. There were clusters here and there, certainly. Some regions were denser than others, but the overall distribution, they believed, was roughly uniform. If you zoomed out far enough, the universe would look the same everywhere, smooth, featureless. A cosmic porridge of galaxies. They were spectacularly wrong. When Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics completed their pioneering surveys in the late 1980s, mapping the positions of thousands of galaxies in 3 dimensions using redshift measurements, the result was nothing like porridge. It was foam. The galaxies were not scattered randomly. They were organized into an unmistakable pattern. Thin sheets and long filaments of galaxies surrounded enormous empty regions. The galaxies clung to the surfaces of invisible bubbles, and the interiors of those bubbles were void. Geller and Huchra had discovered the large-scale structure of the universe, and it looked like the inside of a loaf of bread, or the froth on a cappuccino, or the pattern of soap bubbles in a bathtub. Everywhere they looked, the same motif repeated: dense walls and filaments enclosing empty voids, structure and emptiness intertwined in a cosmic dance that stretched as far as their telescopes could see. They identified a structure they called the Great Wall, a sheet of galaxies stretching over 500 million light-years across the sky. At the time, it was the largest known structure in the universe. It has since been dwarfed by even larger features like the Sloan Great Wall and the Hercules Corona Borealis Great Wall, which stretches an almost incomprehensible 10 billion light-years. But the Great Wall was the revelation. It proved that the universe was not smooth. It was structured, and the voids were as much a part of that structure as the galaxies. Since those early surveys, the picture has been refined with extraordinary precision. The Sloan Digital Sky Survey, which began observations in 2000, has mapped over 3 million galaxies and identified more than 8,000 individual voids. The 2-degree Field Galaxy Redshift Survey mapped over 200,000 galaxies in the southern sky and confirmed the foam-like structure in exquisite detail. Every new survey, every deeper map, every wider scan of the heavens tells the same story. The universe is a web of galaxies surrounding bubbles of nothing, and the bubbles dominate. The cosmic web has 4 basic components. Clusters are the densest knots where multiple filaments converge. They contain hundreds to thousands of galaxies bound together by gravity and bathed in superheated intergalactic gas that glows in X-rays. Filaments are the long, thread-like structures that connect clusters. They are the highways of the cosmos, along which galaxies flow toward the dense intersection points. Walls or sheets are flattened structures that form the boundaries between voids. They are thinner and less dense than filaments, but can extend across hundreds of millions of light-years. And voids are the vast underdense regions enclosed by walls and filaments. They are the dominant component of the universe by volume. Galaxies do not just sit passively on these structures. They move. They stream along filaments at speeds of hundreds or even thousands of kilometers per second, drawn by gravity toward the clusters at the intersections. They fall through walls and slide along sheets. The cosmic web is not a static framework. It is a dynamic living system, where matter flows like water through a network of cosmic rivers, all ultimately draining toward the densest gravitational sinks. And the filaments themselves are far more complex than simple threads. They spin. We discussed in an earlier chapter the discovery of a rotating filament by the Meerkat radio telescope. But that is not an isolated curiosity. Theoretical models have long predicted that filaments should possess angular momentum, that the tidal forces generated by the surrounding cosmic web should set them spinning, and observations are beginning to confirm this. Galaxies within filaments show systematic velocity gradients consistent with rotation. The filaments are not just pathways, They are rotating rivers that funnel matter and angular momentum into the galaxies that form within them. The European Space Agency's Euclid satellite, which released its first survey data in March of 2025, is now mapping the cosmic web with unprecedented precision. That initial data release covered just 0.4% of Euclid's total planned survey area, and yet it catalogued 26 million galaxies. By the end of its mission, Euclid will have charted billions of galaxies across 10 billion years of cosmic history, creating the most detailed three-dimensional map of dark matter distribution ever produced. Early results from Euclid have already confirmed a key prediction of cosmic web theory. More massive galaxy clusters sit at the intersection of more filaments. The most connected nodes of the web, the places where the most threads converge, are where the greatest concentrations of mass accumulate. And clusters dominated by elliptical galaxies, the products of multiple mergers, are more strongly connected to the surrounding filament network than clusters dominated by spiral and disk galaxies. The web does not just scaffold the galaxies, it shapes them. The number of connections a cluster has to the surrounding filaments directly influences the types of galaxies it produces. The cosmic web is the scaffolding of the universe. It is the framework upon which all structure hangs, and the voids are the spaces within that framework. The emptiness that defines the shape of the web, the way silence defines the shape of music. Without voids, there would be no web. Without the web, there would be no galaxies. Without galaxies, there would be no stars, no planets, no life, no minds capable of contemplating the whole extraordinary arrangement. But the web is not forever. We have discussed how the voids are growing, merging, and consuming the filaments from within. We have described the long, slow death of the cosmic web as dark energy stretches the voids until the filaments snap and the clusters are left as islands in an infinite sea. The web is a transient structure, a temporary arrangement of matter that exists only because gravity and dark energy are still roughly in balance. When the balance tips decisively toward dark energy, the web will dissolve and the universe will become what it has always been mostly: empty. But our understanding of this process, our ability to predict what will happen and when, depends entirely on our ability to map the web as it exists today, to measure the voids with precision, to test whether dark energy is constant or changing, to determine whether our models of the universe are correct or whether they need to be fundamentally revised. And right now, the most powerful telescopes and instruments ever built are doing exactly that, mapping the invisible architecture of the cosmos with a precision that could settle the biggest questions in physics within a single decade. Chapter 12: Mapping the Invisible Architecture. At the summit of Kitt Peak in southern Arizona, inside a dome that has been watching the sky since the 1970s, there is an instrument that can measure the light of 5,000 galaxies simultaneously. It is called the Dark Energy Spectroscopic Instrument, or DESI, and it is building the most detailed three-dimensional map of the universe ever created. DESI works by threading fiber optic cables to precise positions on a focal plane, each fiber aimed at a different galaxy. Light from each galaxy travels through its dedicated fiber to a spectrograph that splits it into its component wavelengths. From that spectrum, astronomers can determine how fast each galaxy is moving away from us, and therefore how far away it is. Do this for 5,000 galaxies at a time, night after night, month after month, and you build a map of the universe in 3 dimensions that reveals the cosmic web in breathtaking detail. DESI's first-year data, released in April of 2024, mapped the positions of millions of galaxies and quasars stretching back over 11 billion years of cosmic history. The results already shook the foundations of cosmology. Using baryon acoustic oscillations, those ancient sound wave imprints frozen into the distribution of galaxies like ripples on a pond, DESI, measured the expansion history of the universe with extraordinary precision, and the results hinted at something unexpected. dark energy may be changing. The standard model assumes that dark energy is constant, the cosmological constant, a fixed value that does not change over time. But DEC's data showed slight but statistically significant evidence that dark energy may be weakening, that it was stronger in the past and is becoming less potent as the universe ages. If confirmed, this would be the first credible challenge to the cosmological constant since its discovery in 1998, and it connects directly to everything we have discussed. If dark energy is evolving, the timescape model becomes more plausible. If dark energy is growing stronger, the Big Rip scenario becomes more likely. If dark energy is weakening, the fate of the universe might be radically different from what current models predict. The answer depends on what DEC and its successors find in the coming years. Meanwhile, in orbit around the Sun, 1.5 million kilometers from Earth, at a location called the second Lagrange point, another instrument is transforming our view of the dark universe. The Euclid Space Telescope, built by the European Space Agency and launched in July of 2023, is designed to do something no telescope has done before. It is creating a three-dimensional map of the distribution of dark matter across the cosmos by measuring the subtle distortions that dark matter's gravity imposes on the shapes of background galaxies. This technique is called weak gravitational lensing. Every galaxy's image is slightly stretched and warped by the dark matter between it and us. By measuring those tiny distortions across billions of galaxies, Euclid can reconstruct where the dark matter is, how much of it there is, and how it is distributed in the cosmic web. Euclid's first survey data, released in March of 2025, covered just 0.4% of its total planned survey area. And yet, it catalogued 26 million galaxies with enough precision to confirm key predictions about the relationship between galaxy clusters and the cosmic web. The full survey will cover 14,000 square degrees of sky, roughly 1/3 of the celestial sphere. By mission's end, Euclid will have measured the shapes and positions of billions of galaxies stretching across 10 billion years of cosmic history. The Euclid flagship simulations, enormous computational models of the cosmos, have already generated 3.4 billion simulated galaxies to calibrate what the real data should look like if the standard model is correct. When the actual observations are compared to these simulations, any discrepancies will point to problems with the model, and one of the most sensitive tests involves the shapes of voids. In a universe with the correct recipe, the right amounts of matter, dark matter, and dark energy, voids should have specific average shapes when their measurements are statistically stacked. If you take thousands of voids and average their shapes together, the result should be close to spherical if the model is right. If the stacked shape is elongated or compressed, something is wrong with the recipe. Something fundamental about the universe's composition is different from what we assumed. And that is where the Nancy Grace Roman Space Telescope comes in. NASA's Roman telescope, scheduled for launch in the coming years, will have a field of view 100 times larger than the Hubble Space Telescope. It will be able to detect and measure tens of thousands of individual cosmic voids, some as small as 20 million light-years across. By statistically stacking these voids and analyzing their shapes, scientists will perform one of the most powerful tests of dark energy models ever attempted. Alice Pisani, a cosmologist affiliated with the French National Center for Scientific Research and Princeton University, has said it directly. By studying voids, we should be able to put powerful constraints on the nature of dark energy. Voids are among the cleanest laboratories the universe provides. Unlike galaxy clusters, which are complicated by baryonic physics, cooling flows, feedback from supermassive black holes, and a dozen other messy processes, voids are simple. They are mostly empty. Their physics is dominated by gravity and dark energy, with minimal contamination from the complex astrophysics of star formation and galaxy evolution. That simplicity makes them ideal for testing fundamental cosmological models. And from the ground, another instrument is joining the effort. The Vera C. Rubin Observatory, currently under construction in Chile, will conduct the legacy survey of space and time, scanning the entire visible southern sky every few nights for 10 years. It will discover an estimated 20,000 supernovae in its first 5 years alone. Those supernovae, each one a cosmic measuring stick, will provide independent measurements of the universe's expansion history that can be cross-checked against DESI's baryon acoustic oscillation data and Euclid's lensing measurements. Together, these instruments represent the most ambitious, coordinated assault on the mysteries of dark energy, cosmic expansion, and the large-scale structure of the universe ever undertaken. They are measuring the voids with a precision that would have been unimaginable a decade ago. They are mapping the invisible scaffolding of the cosmos with tools that can detect the faintest distortions in the fabric of space-time. And what they reveal may rewrite everything we think we know about the universe. Because right now, in 2026, cosmology is in crisis. The Standard Model is creaking under the weight of accumulating anomalies. The Hubble tension refuses to resolve. The cold spot refuses to be explained. DESI's data hints at evolving dark energy. The timescape model challenges the very existence of dark energy. The KBC Void challenges the homogeneity of the universe. And voids, the emptiest and most overlooked structures in the cosmos, are at the center of every possible answer. The instruments are deployed, the data is flowing, and what it reveals next could change the story of the universe forever. Chapter 13. The Race to Understand Nothing. We are living through what may be the most turbulent decade in the history of cosmology. Not since the 1920s, when Edwin Hubble proved that the universe was expanding and shattered the static model that had prevailed for centuries, has the foundational framework of our understanding of the cosmos been under such sustained assault. And the assault is coming from every direction at once. Let us take stock of where things stand. The Standard Model of Cosmology, Lambda CDM, has been the reigning framework for over 2 decades. It describes a universe composed of roughly 5% ordinary matter, 27% dark matter, and 68% dark energy. It assumes that the universe is homogeneous and isotropic on the largest scales. It assumes that dark energy is constant, described by the cosmological constant lambda, and it assumes that the expansion of the universe is accelerating and has been for the last 5 billion years. This model has been spectacularly successful. It explains the cosmic microwave background with extraordinary precision. It predicts the large-scale distribution of galaxies. It accounts for the abundances of light elements formed in the Big Bang. It is, by almost any measure, the most successful cosmological model in the history of science. And it is cracking. DESI's first-year results, released in April of 2024, produced the first credible evidence from baryon acoustic oscillation data that dark energy may not be constant. The signal is subtle. It sits at the boundary between suggestive and significant, but it points in a direction that the Standard Model does not easily accommodate. If dark energy is evolving, if its strength changes over time, then Lambda CDM needs to be modified or replaced. And the full DESI dataset, accumulating as we speak, will push this question toward a definitive answer within the next few years. Then there is the Hubble tension. We covered this in detail earlier. The local measurement of the expansion rate disagrees with the cosmic microwave background measurement by a margin that has grown more statistically significant with every improvement in precision. The gap is now at the level of roughly 5 sigma in some analyses, which in physics is the threshold for claiming a discovery. This is not a minor discrepancy that can be waved away with better calibration. Something is genuinely wrong. Either one of the measurements has a systematic error that no one has been able to identify despite years of searching, or our model of the universe is missing something fundamental. The KBC Void hypothesis which proposes that our local cosmic neighborhood is less dense than average and inflates our expansion measurement, offers one possible resolution, but it comes with its own price. A void that large and that deep is itself incompatible with lambda CDM, creating a tension at the level of 6 sigma. You cannot fix the Hubble tension with the KBC void without breaking the standard model, and you cannot explain the KBC void within the standard model without ignoring the Hubble tension. The two problems are entangled. They may be the same problem. And then in November of 2025, a team of physicists at Yonsei University in South Korea published a paper that went even further. Junhyuk Son and his colleagues argued that there is a systematic bias in the way we use Type 1, a supernovae, the standard candles that led to the discovery of cosmic acceleration in the first place. Their analysis focused on something called progenitor age bias. Type 1a supernovae occur when a white dwarf star in a binary system accumulates enough material from its companion to trigger a thermonuclear explosion. But not all white dwarfs are the same age. In the distant past, when the universe was younger, the average white dwarf progenitor was younger too, and younger progenitors, the Korean team argued, produce slightly dimmer explosions. This matters enormously, because the entire measurement of cosmic acceleration depends on comparing the brightness of nearby supernovae to the brightness of distant ones. If distant supernovae are systematically dimmer than expected, not because the universe is accelerating, but because the progenitors were younger and intrinsically fainter, then the apparent acceleration could be an artifact, a measurement bias masquerading as a fundamental feature of the cosmos. Combined with DESI's baryon acoustic oscillation data, Son and his colleagues argued that the universe may have already transitioned from accelerated expansion to decelerated expansion. In other words, the universe is not speeding up anymore, it is slowing down. If validated, this would mean that the 27-year-old consensus on cosmic acceleration, the discovery that won the Nobel Prize, the foundation on which 68% of the universe's energy budget rests, was based on a misinterpretation of the data. This is an extraordinary claim, and extraordinary claims require extraordinary evidence. The Korean team's analysis has been met with skepticism by much of the cosmological community. The progenitor age effect they describe is real, but whether it is large enough to explain the full apparent acceleration is fiercely debated. Independent tests using different supernova samples, different calibration methods, and different statistical techniques will be needed to confirm or refute the claim. The Vera Rubin Observatory's 20,000 supernovae over the next 5 years will be a decisive test. Now step back and look at the full picture. If the timescape model is right, dark energy does not exist. The acceleration is an illusion caused by the lumpy structure of the universe and the different rates at which time flows in voids and dense regions. If the Korean team is right, the universe is not accelerating at all. The supernovae that seem to prove acceleration were systematically biased. If the KBC Void hypothesis is right, our local expansion measurement is inflated by the underdensity we live in, and the true expansion rate is the lower value from the cosmic microwave background. Any one of these, if confirmed, would be a revolution. All three together would represent the largest paradigm shift in cosmology since the discovery of the expanding universe itself. And voids, the emptiest, most overlooked structures in the cosmos, would be the reason everything changed. The standard model is not dead. It has survived challenges before. It is supported by an enormous body of evidence, and the anomalies we have described, while striking, are not yet definitive. Science moves slowly and carefully for good reason. Extraordinary claims are held to extraordinary standards. The burden of proof on the challengers is immense. But the challengers are not going away. They are getting louder. Their data is getting better, and the questions they are asking are the right questions. Is the universe really homogeneous on the largest scales? Is dark energy really constant? Is the expansion really accelerating? Are our standard candles really standard? Euclid's first full data release and the continuation of DESI's survey will be critical tests. So will the Vera Rubin Observatory's supernova harvest. So will the Roman Space Telescope's void census. The answer may arrive within this decade. It may arrive within the next 5 years. We are standing at a precipice. On one side is the model we have trusted for a quarter century. On the other side is something unknown, something that may be more beautiful, more elegant, and more true than what we have now, or something that confirms what we already believe with even greater precision. Either way, the voids will tell us, because they are the largest structures in the universe. They dominate its volume. They drive its expansion. They shape its fate. And they are, right now, the key to unlocking the deepest secrets the cosmos has left to reveal. Chapter 14. What it means to live in a universe of nothing. We have traveled a long way tonight, from the absolute darkness of the Boots Void to the quantum whispers that created it. From a Nobel Prize-winning discovery that may be wrong to a cold scar on the oldest light in the universe that no one can explain. From the last star that will ever be born to a tiny blue galaxy burning alone in the dark. Now let us sit with what we have learned. Nicolaus Copernicus showed us that the Earth is not the center of the solar system. We orbit the Sun. That was humbling enough. Then astronomers showed us that the Sun is not the center of the galaxy. It is an ordinary star in the suburbs of an ordinary spiral galaxy, 2/3 of the way out from the center, in a relatively quiet arm far from the action. Then Edwin Hubble showed us that the Milky Way is not the center of the universe. It is one galaxy among billions, scattered across an expanding cosmos with no center at all. Then the cosmic web was discovered, and we learned that our galaxy sits not at a grand intersection of cosmic filaments, but on the thin wall of a bubble, a membrane between voids. And then the KBC Void was characterized, and we learned that even our bubble is less substantial than average. We live in a region of the universe that is underdense, below the mean, emptier than it should be. Every step in our cosmic understanding has made us smaller, more peripheral, more ordinary. Every time we thought we occupied a special place, science revealed that we did not. Copernicus began the process, and the voids may complete it. Because what voids tell us is not just that we are small or peripheral. They tell us that most of reality is not just indifferent to us. It is empty of anything at all. 80% of the observable universe is void. The galaxies, the stars, the planets, the civilizations, the love songs, and the mathematics, all of it clings to the thin walls of bubbles floating in an ocean of nothing. The nothing is the dominant feature of the cosmos. It is not the background, it is the foreground. We are the anomaly. Complexity, structure, light, life. These are the rare exceptions. The universe's default state is emptiness. A being born at the center of the Boots Void would have no evidence that the rest of the universe exists. No galaxy visible, no cosmic web detectable. Just their own galaxy, alone in a darkness that stretches 330 million light-years in every direction. They would develop physics, they would build telescopes, and they would conclude with perfect logic and flawless data that their galaxy is the only thing in existence. They would be wrong, but they would have no way of knowing it. In the far future, this will be the condition of every civilization. As the voids expand and the cosmic web dissolves, the observable universe will shrink for every observer until only their own galaxy remains visible. The rest of the cosmos will have slipped beyond the horizon. Any intelligence born 100 billion years from now will look out at a sky containing exactly one galaxy and will never know that the universe once blazed with 100 billion more. The evidence will be gone, unreachable, erased by the expansion of the very voids we have spent tonight exploring. The void is not just the future of the universe, It is the natural state. The cosmic web is the interruption, the brief flowering of structure between the Big Bang and heat death, a temporary arrangement of matter that exists for an eye blink of cosmic time before the voids reclaim everything. And yet the fact that anything exists at all in this ocean of nothing is the most extraordinary fact in physics. Quantum fluctuations, smaller than an atom, grew into a cosmic web that stretches billions of light years. From that web, galaxies formed. In those galaxies, stars ignited. Around those stars, planets coalesced from dust and gas and debris. And on at least one of those planets, orbiting an ordinary star in the suburbs of an ordinary galaxy, on the wall of an ordinary void, matter organized itself into something that could look up at the emptiness and ask the most audacious question any arrangement of atoms has ever asked. Why is there something rather than nothing? The void does not have an answer. The void has never had an answer. The void is not a thing that answers. It is the absence of things. It is the space in which questions dissolve unanswered. But the question exists, and the fact that it exists, the fact that there are minds in this universe capable of contemplating the emptiness, of measuring it, of mapping it, of being terrified and awed by it, that is a consequence of the emptiness itself. Without the voids, there would be no cosmic web. The voids are what define the structure. The emptiness is what gives shape to the fullness. If the universe had been perfectly uniform, if there had been no quantum fluctuations, no slight underdensities growing into vast empty cavities, then there would have been no filaments, no walls, no clusters, no concentrations of matter dense enough to collapse into galaxies, no galaxies forming stars, no stars forging the heavy elements that make planets and people possible. The nothingness was necessary. The void is not the enemy of existence. It is the architecture of existence. It is the negative space in the sculpture, the silence between the notes, the darkness that makes the light visible. Without the voids, the universe would be a featureless fog of uniformly distributed hydrogen. No structure, no complexity, no life. No one to wonder at the beauty of a spiral galaxy or the loneliness of a dwarf galaxy burning blue in the cosmic dark. We are temporary. Everything we have ever built, every civilization that has ever risen and fallen, every thought that has ever been thought, occupies a sliver of cosmic time, so thin that in the long run it rounds to zero. The voids will outlast us. They will outlast the stars. They will outlast the galaxies. They will outlast the cosmic web itself. When the last star winks out in a void galaxy 100 trillion years from now, the universe will finally return to the only state it has ever truly preferred. Quiet, dark, and infinite. The great nothing was always the destination. We are the detour. But what a detour it has been. From quantum whispers to galactic superclusters. From the first light of the cosmic microwave background to the last firefly in the local void. From minds that evolved on a rocky planet to instruments that can map the invisible skeleton of the cosmos. We are made of star stuff, as Carl Sagan said, but we are also made of void stuff. The emptiness shaped the web shaped the galaxies shaped the stars shaped us. We are, in the most literal sense, the voice of a universe that is mostly silence. And that voice, however brief, however small, however easily lost in the vastness of the great nothing, is the most remarkable thing the voids have ever produced. If you enjoyed this journey through the emptiest places in the cosmos, please like this video and subscribe to the channel. Your support makes these deep investigations possible. Tell me in the comments, what unsettles you more? The idea that dark energy might not exist, or the idea that the universe will eventually become nothing but void? And what should we explore next? These are not just questions for physicists, they are questions for all of us. Because the void is not out there somewhere, far away, irrelevant. The void is here. We live inside one. And it is getting bigger every second. Thank you for listening. I will see you in the next journey.